universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to Sky Tour Radio. This is Mark D'Antonio here, and we have over there, we have Amanda, and you see down below me, we have Tara, and over there, we've got Daryl. How are you guys? Hi, Tara. How are you?
Hi, great. Glad to be here.
Yeah, it's great. I'm glad you're here. Amanda, how are you?
I'm well, thanks. How are you?
Fine, thank you. Daryl's over there in the corner. How you doing?
I'm fine, Mark. Ho, ho, ho.
Ho, 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 indeed. It's so nice to see you guys. Hopefully we'll have a fun show tonight. We're going to be talking about some really cool things in the universe tonight because that's what we do. It's an astronomy show. If you notice my hat, we are going to be talking about extraterrestrial life as well, which is why the alien in the middle there. It's pretty cool. And we're going to be talking, of course, because it's the holiday season, we're going to be talking about the Christmas star. But we'll get to that in a moment. I just want to mention that Sky Tour Radio is an offshoot of Sky Tour Livestream, which is our live deep sky observatory, which couldn't have happened without that person down there, Tara, right there, and Marianne Robb, who is one of our staunch supporters and benefactors as well. And we have Daryl with us on the streams, and hopefully Amanda again soon. And we take the live imagery from the night sky and all the stuff we show in Sky Tour Livestream, except for where I tell you on the radio show here, Sky Tour Radio, everything we show was imagery that was taken in our observatory. So there's no copyright issues. We don't have to worry about any of that because it's all our stuff, man. And we do this because we love doing this. I love this particular brand of public outreach. And Sky Tour Livestream is free. And we also have a free online server where you can go and see all the photos we've taken with this telescope system, or all of our telescope systems actually, and enjoy them, take them down, use them as wallpaper. And it's all, for no cost. You guys go have at it. You can go to my Facebook page and check out the static link, which takes you to the static server. And you can go to the Sky Tour Livestream Facebook page and see the link there. And go check out the imagery. It's all available and it's all free. We love to go check out nebulae in the sky. In fact, we're going to look at nebulae tonight that we took with the Sky Tour Livestream telescopes. And the skies are just stunningly beautiful where the telescope is located. And that means that we get among the best shots. And Daryl over there has been with me for a lot of the times when we actually haven't been on the air live on streaming, just to do testing and so forth. And he's watched the way the telescope and the results have changed over the last few months. They've gone from good to better to sometimes holy cow,
As Beavis once said, almost there, dude.
Whoa, that was cool. Yeah. So, we have a couple little extra nagging things, but the imagery for the most part looks beautiful. And so we'll show you some of that tonight. I've worked out ways. You know how we had these big halos around the star images? Well, those are going to be gone now because I figured out a way to get rid of the halos using programmatic means. That is to say, something that we had to program it right. And so now it's pretty neat to see how this all comes together. And honestly, what you see in the telescope is almost what you get as the final processed image. So those are beautiful in their own right. So, hey, it's Sky Tour Livestream. It's on YouTube. Join us if you haven't. It's a lot of fun. And we have a lot of people from all over the world who join us. So, be one of the many, and be one of the folks that can hang with us. And for some of you, we're starting a program where some of you can join us on the air and hang with us and check out the things firsthand and actually ask questions one-on-one, with us on the air. So you don't actually have to sit there and type it in chat and hope someone sees it. You'll be right there with us. And we've done that already with a couple of people already, and we're going to do that, I think, with a lot more. It seems to work out well. So this is Sky Tour Radio, and I want to welcome you to our radio show and our live stream. You can see us on KGRA DB, KGRA Radio DB, or is it KGRADB.com? And you can see us on YouTube at KGRA DB channel. And you can also listen to us on KGRAradio.com. So we're all over the place, And that said, it is the Christmas season. And I wanted to start off. Okay, Tara's dotting, yes, I wanted to start off because one of the things that everybody always says and wonders is, what could the Christmas star have been? Remember the Star of Bethlehem that the wise men supposedly saw and followed? What was it they were looking at? Now, if we take it that it's more than just a myth, if it was actually an event that kicked off other events, what could it have been? And there's a number of things it could have been. And there are interesting conjunctions of the planets that could have happened back then. Extraordinary bright appearances of Venus. So there's a lot of those things. And I'm not going to be able to give you any answers because we don't really know, because we don't know what it was they looked at and what they saw. But I can tell you that one of the things that we saw in SkyTour Livestream is we saw this. This was the planet Jupiter at the bottom and the planet Saturn at the top in the same field of view. Daryl, I think you were with us on that.
I was.
You remember that? That was pretty cool to see those two planets at the same place in the sky almost.
It was. That doesn't happen very often. So it was extra special.
Yeah,
well, you
it
can
was.
see the moons and the rings. It's very cool.
That was a stunning picture.
Oh my God.
Yeah, and for people to think this was a composite where you took one picture and put in another, no, this was exactly what we saw in the SkyTour Livestream telescope. And everybody that attended this stream saw it live, just like that. Cool. And that's the purpose of that particular stream, was to show this beautiful apparition known as a conjunction of Jupiter and Saturn. And that, what we're looking at right there, was actually pretty bright in the sky. And it's possible that this was the Christmas star, because this type of conjunction has occurred before. And at around the time when this supposedly happened, I think that the time frame works out that there was one such conjunction at that time. And that would be kind of interesting. Daryl, I don't know if you have any more information on that or not, but I throw it at you for more info if you've got it.
Well, not that in particular, but conjunctions happen, and I've seen triple conjunctions where we will have three planets in the sky at once. I saw the grand alignment way back in the day. All the bright planets were strung across the sky like pearls on a necklace.
Yeah,
really cool. You could actually see something sort of like that right now.
Yeah, exactly right. And we saw Venus, we see Saturn, and we see Jupiter in the sky right now. In fact, when we
Mercury's popping up to join them too.
That's true. That's true. If you're out early enough, just after sunset. But during the deep dive with Daryl, folks, he'll probably show you that as well. And he's gonna talk about a few other cool things as well. We're gonna get to that. That's pretty cool. And the other thing too that it could have been is this guy. Okay, this is Venus as seen through the SkyTour Livestream telescope. Venus shows phases, kind of like the moon does, because it's closer to the sun than we are. So we actually can see the sun lighting it differently as it goes around, closer to the sun from us. All right. So these phases, Venus can become a very, very thin crescent, and then it could also become big and round. Although smaller in the sky, it's actually bright because it's the full face of Venus. This, when you see Venus as a crescent, it's actually quite big in the sky, but not as much of it's being illuminated. So you can be confused as to how bright it is relative to when you see it almost like a fully lit up ball.
There's kind of a trade-off how much of a crescent phase is lit versus how close Venus is to us at the time. It continues getting brighter because it's getting closer, but there will come a point when that crescent gets so skinny that even though it's at or near its closest to Earth, right before it passes between us and the sun, it's called an inferior conjunction, that Venus will start dimming. But it's still at about maximum brightness right now, minus 4.7, I believe.
Yeah, I got a case within the Mutual UFO Network just the other day where someone took a picture of Venus, and off to the left in the trees on this particular date, he had captured these lights. And I mentioned to him that those lights are exactly where the moon was. It was a very small waxing crescent. And, he's insistent it wasn't the moon, but it was there for a long, long time. And so it sort of smacks of astronomical object. So it's interesting how these things look to people, how people interpret them. And if you went out just after that date, a couple days later, you would see Venus, you'd see Saturn, and then you'd see Jupiter, and then the moon. And it was really just so cool to watch. And what you're actually looking at is the plane of our solar system. The plane of the solar system. They all move in the same plane. We're actually going to be talking about that a little bit tonight when we talk about how the solar system formed. There's a discussion that follows this, pretty cool. And that plane is called the ecliptic. And I think Daryl will probably mention it too when he goes into the deep dive in a little while. Mm-hmm. So I think that's pretty neat. But again, because it's Christmas, we thought we'd try to figure out whether it was a conjunction of two bright planets or more, or was it just Venus being seen, or was it actually something else? Now, that something else could have been a supernova of sorts, but we don't know of any supernovae that went off around that time that might be responsible for this, especially looking in that particular direction. But it would be visible in the day and it'd be visible in the night. When Betelgeuse, for instance, goes supernova, and that Betelgeuse, remember, is the upper left-hand star in Orion. When that goes supernova at some point, it'll be visible in the daytime, a daytime star, and it will be visible at night, of course. In fact, you'd probably see your shadow by it at night. That's the truth. And the Crab Nebula is a wonderful nebula that is near one of the horns of Taurus the Bull in the constellation of Taurus. And the Crab Nebula was a supernova that took place in 1054 AD, and it was noted by Chinese astronomers. And it, too, for a few months, was visible during the day as a star during the day. And then, of course, it faded from view as the months went by. But the fact of the matter is, nowadays, we actually see the results. We see this beautiful, expansive cloud of debris that's slowly moving away from the location where the supernova occurred. And it left behind a pulsar, which is a special type of dead star called a neutron star that has like lighthouse beacons on its surface. They're actually hot spots, and they spin very rapidly. And as they spin, those hot spots can flash by us. So it's like, as it goes by, we'd see it. And the Crab pulsar spins over 33 times per second. And that's a whole star, the core, leftover star core, that's about the size of Manhattan Island, something like 12 miles or so. That's actually quite an achievement. So the universe has a lot of odd things it throws up to offer us, And I'll say one thing. When Tara asks her questions that we'll hear later, okay, her questions are usually of many of these odd things that we've never heard before, and that she wants to see answered, I'm sure you have some good ones for us tonight, Tara. Yeah.
Well, that's a matter of opinion, but I think there's so much to know, and
Right.
I'm very interested. So it's all cool.
Yeah, and I have to mention, for instance, okay, this one over here, the one who's quiet right now, Amanda. She said, "Oh no, don't call on me." Okay, well, she actually, when she first started with us in SkyTour Livestream as the co-host, you were the only co-host of SkyTour Livestream with me. And when she started with me, she knew nothing about astronomy. And now she could tell you what this diagram is right now. This is how we classify stars.
I'm sure a stipulation in my contract is no sudden pop quizzes.
But this is something that you know. And
that's the spectral classification. I can never remember the name. Hertzsprung.
Hertzsprung Russell.
Yeah.
You got it. It's a Hertzsprung Russell. You're almost there.
7 years. I mean,
yeah. Right. And, she can tell you how most normal stars operate, right? They're the ones on the left side are a certain color. The ones on the right side are a certain color. And I'm sure that you can tell us what that means, Amanda.
Is that my cue? I can. Would you like me to?
I would love it.
Well, as you can clearly see, the ones on the left for those viewing are bigger and bluer and hotter. But again, that's a relative term. The ones on the bottom right are smaller and red and cooler, but still extremely hot. And then we are, let's try this again, folks. G is either a 5 or an 8. A 5?
G2.
Oh, okay, G2.
And the confusion with the 5 has to do with where in the diagram we are. That snaky line that goes from the upper left to the lower right, that has a designation with the Roman numeral 5, which is a V. Okay. And they're called dwarfs. All right. And even big stars, even big hot blue stars that would basically dwarf our sun are also dwarfs if they're converting hydrogen to helium like most stars. But yeah, this is the Hertzsprung-Russell diagram. And
I only mentioned that to give you some kind of indication. If we're kind of in the whitey, yellowy kind of spectrum as a G, and that's our sun, and think how big and bright that is. Think how far that light and that heat carries into our solar system, and then think we still have F, A, B, and O to contend with that are even bigger and hotter,
That's right.
So, when we say the red ones are smaller and cooler, again, it's all relative. And these numbers get big fast. So,
if you look at the luminosity scale on the left, it's in solar units, how bright the sun is. And if you find the number 1 on that scale and then go to the right, that's where the sun is, right in the middle. On the right side, as far as left to right goes, temperature, but on the solar brightness scale, that's the sun right there at one unit of brightness.
Right, and if you look up the top of that scale that Daryl just mentioned, you see 10 to the 6th. Now that is a million. That's a 1 with 6 zeros after it. That means 1,000,000 times brighter in total output of energy. Okay. And when you get the stars that bright and that hot, much of their energy is coming out in the far end of the blue spectrum, including the ultraviolet, which is where you get your tans, guys. And if you want to go get a real tan, 7 seconds in front of an O star should do it for you.
I'd be looking real good, huh?
But 8 seconds and you've got 3rd-degree burns. So I would probably, I'd probably avoid it like the plague, to be honest.
You look like Kentucky Fried Chicken if you stay out too long.
That's right. And several successive exposures, Tara, and you'll have that nice leathery skin that you see on that one person who you always see at the beach who just has been out there every day of their lives for the last 50 years.
Sounds like my sister-in-law.
Okay, see, we all have one in our family, don't we? Yeah. Yeah. So this is the Hertzsprung-Russell diagram. And why am I bringing it up? Well, because when we see stars that are born, many times they're born basically anywhere along this diagram, all right, along the snaky line. That's where they all start, along that snaky line down the middle. Okay, so you can have a hot blue O-type star, which will last maybe 5 million years or less even. The hottest ones only last a few 100,000 to 1,000,000 years. And so obviously, and maybe not so obviously, you could never have life develop there. Life takes a long time to develop. So why do those stars actually exist? What there's a lot of mass. There's a lot of hydrogen gas that gets collected and contracted down to the cores of these large gas clouds, and that makes these stars. And when they wink on, it means that hydrogen fusion can commence. And usually that means when it reaches a temperature of something called 13 million Kelvin. That is an extremely high temperature, and it's something that I guess you'd want to stay away from, to be honest with you. But that's the lowest temperature at which you can have hydrogen fusion. And these stars generally have temperatures that allow them to do other types of fusion. There's only 2 types of fusion that we know of in the entire universe, and they can do both types when they're that massive. Coming down the line to when you get to a star like the sun, well, we do hydrogen to helium fusion, and maybe we can fuse carbon into nitrogen or helium into carbon. And I'm referring, of course, to this guy, the periodic table of the elements, that nemesis to everybody who goes through high school, and they've seen this. But this kind of shows where elements come from. In the purple, merging neutron stars create those elements. The green, well, older stars like the sun when it dies, stars about the same mass, that's the type it will produce those elements. And the yellow, well, that happens in supernovae. Those are created in supernovae. All right. Now, that chart wasn't meant to scare you, okay? But it is something that is near to my heart and dear to my heart, okay? Because knowing how the elements work in the universe is so important to understanding how life forms in the universe. And that's what this is all about today, is trying to figure that out. Now, when we look at things that we've seen with Skytour Livestream, we tend to look at the really, really pretty objects. Okay, for Christmas we have this one. This object here we took with the Skytour Livestream. Okay, Amanda, you're not going to know this. Tara, you may not know this. Daryl will know this, I'm sure. The object of interest is, in this case, at the top in the blue. Okay, this is the Christmas tree cluster.
Yep.
Okay. And as I suspected, of course, you know that, Daryl. And down
And
below,
is it upside down?
It is.
It is, yes.
That's why I didn't recognize it offhand.
Well, then I guess I should have flipped it upside down. But I have to show it the way it looks in the sky.
Absolutely.
And if you notice in the dead center, you see that cone-shaped dark nebula there. That's the interesting element to me. But that cluster at the top, hot young stars, and they're also hot enough to cause the hydrogen gas around them to glow red. Okay. And then on top of that, there's a lot of dust in this area too. Now, see, dust is the life giver to the universe. Dust is where it's at. So when we talk about this show being the dark corners of the universe, dust is the most important part of the universe. It's not the gas, it's the dust, because you're made of all that dust. Every bit of it is inside of you. That all the atoms that you have inside of you came from this dust that's in the universe, and it's quite prevalent in the universe. But we take pictures of beautiful things like this all the time, and you might see some of the dark dust in there. You can see little dark lanes throughout. Okay, and then this one's even more obvious. This is called the Gamma Cygni Nebula. It's in Cygnus, the swan, which is directly overhead in the summer. And you can't see it with your eye, but you can see it with a telescope. And this, of course, is just a few second exposure in our telescope. And you see the dark objects, right? You see there's 2 bright patches of reddish orange gas. That's ionized hydrogen glowing because of the star to the right there. That's Satyr. That's Gamma Cygni. And in between those two reddish patches, you see a dark area. Well, that dark area isn't a void in the hydrogen. It's actually a dark layer of dust that's in front of the hydrogen gas and blocking it behind it. See? So we have this stuff everywhere. It's amazing how this material is so common in the universe. And it's also so very important to life in the universe, right? And when we look at these different objects, they all have in common, they all have this dark strands of dust, okay? And usually it means that they're part of these gigantic complexes of dark nebula. But what's in them? You know, it's found whether we're looking in galaxies, like the Andromeda Galaxy, or whether we're taking photos of our own galaxy, like this. You can see in the center of this right here, you look down the center of that, and when it goes up and down, you actually see the dark modeling. That's dust in our own galaxy, dark lanes. And that dust is part of what are called giant molecular cloud complexes. And you have to understand that when the universe was first formed, there was hydrogen and helium and some lithium. Okay. And that was it. But when large stars were formed and they went supernova, they distributed a lot of their internal composition to the universe. And many, many billions and trillions of supernovae occurred over time. And a lot of this dust can be made during those explosive outbursts. And that's kind of interesting. And the thing that's interesting also is that this dust, when we talk about this dust, you think of dust in the air or whatever, like in a sunbeam, you see dust in the sun. And you say, wow, well, that's, got a lot of dust in my house. You pat a, couch cushion and poof, you get all this stuff in the air, right? Well, that's millions of times more dense than the clouds of dark dust that we see in the universe. Okay, millions of times more dense. When we see these dark dust clouds, you got to understand these are massive, and we're seeing them from far away. Our sun could be immersed in a gigantic dark cloud, and we don't even know it. That's a possibility. But where we see these dark dust in the universe, okay, like in this object here, okay, or actually, if you look at Orion, this is an image that Daryl sent to us last time. You can see lots of this glowing hydrogen gas in the constellation of Orion, but you also see dark dust in here as well. Well, this dark dust is very, very, very dense for the interstellar medium. And you know how much that means? That means 100 to 300 molecules per cubic centimeter. Cubic centimeter. 100 to 300 molecules. Consider that the air you're breathing right now and watching this show on has 25 times 10 to the 18th molecules per cubic centimeter. And now you can see a vast difference between 100 and 300 molecules. But when you've got so much of it over such an expansive distance, from a distance, you can see it. It looks pretty interesting, And the temperature in these regions is very cold. It ranges from about 7 to 15 Kelvin. What's that mean? 10 to 100 Kelvin, okay, is another value. That's minus 263 to minus 173 Celsius, or minus 441 to minus 279 Fahrenheit. I mean, it's viciously cold. But see, in absolute zero in the Kelvin scale is minus 273 Celsius, or minus 459 Fahrenheit. Okay. And these clouds sit at about 10 to 100 Kelvin. All right. The Kelvin scale was created because we wanted to have a scale where we could start at zero and not have to worry about negative values. Okay. There's no minus 10 Kelvin technically. So 0 is absolute 0. It can't get any colder than that. Although there's research to indicate that there's possibilities.
Otherwise, the scale is the same as Celsius, is it not?
It's minus 273. Yeah. It doesn't match Fahrenheit at all because Fahrenheit's got to be weird. It's the weird conversion, you know. When you look at Kelvin, okay, if you want to know what the Kelvin scale is, you just take 273 off, okay, and you've got your Kelvin value. All right. So one of the things that's interesting about these scales of temperature is that these are just things that astronomers do, well, basically not to confuse you, but it does confuse you. I apologize for that. It does happen. So one of those things that is important too is that these regions of dark dust have these very low temperatures. And inside some of these nebulae, such as this guy, okay, this is one we took. This is the Rosette Nebula. It's to the left of Orion. The Rosette Nebula has a lot of dark, tiny little globules in it. And this is a close-up of one region. And right there in the middle, you can see two little black dots. Those are called Bok globules. When I was getting my astronomy degree, Bart Bok was teaching us about dark globules, as a matter of fact. And I found it was probably the most fascinating lecture I've ever heard because he was talking about these and saying, well, you know, they're only about 3 light years or less, and they contain about 2,000 solar masses. Well, what's that mean? Okay, it means that they are focused concentrations of this dark dust in the universe. And this dark dust in the universe is where new stars are going to form and where new planets may form. All right. Now, at the time, we didn't know for sure that planets could form there. I remember raising my hand and saying, Dr. Bok, can't planets form there too? And at the time, we didn't know of any planets at all. Okay. And his response was, I don't see why that's not possible. So he was a forward-looking guy. He actually knew that there was potential there. And I respected that answer because I always thought that, you know, these dark areas are actually where it's at. Turns out that's true. It is where it's at. You know, they're a gravitationally condensing area in space, right? And as it condenses, it comes in from all sides, right? All sides, from every direction, this material is coming in. But material coming in has motion to it. And as a particle is going this way, if there's a concentration of gravity over here, say right here, and a particle is going by like this, it's going to get tugged in by the gravity of the other stuff. And it's going to change its direction and start curving on a curved path. Okay. And that gives it something called angular momentum. And angular momentum isn't a class we're going to be having anytime soon, I promise. But all it means is that the angular momentum ends up causing the material to fall in from all sides, but ends up leveling out in one plane and going around the star in one direction. Okay. And that is what we call an accretion disk. We see them all over the universe. Okay. We know that our solar system developed one. And the remains of it, you can see when we talked about those planets. You had Venus, Saturn, Jupiter, the moon. They're all in our ecliptic plane. Well, that ecliptic plane is also the remains of our accretion disk. And the zodiacal light, that glow that we see of dust that's backlit by the sun that we see a couple times a year. And we've showed several times on SkyTour Livestream and SkyTour Radio. That dust is also the backlit remains of what used to be the accretion disk before the planets formed and started sweeping up all this additional detail and debris. So these accretion disks, you know, in the very beginning probably looked kind of like this for our sun. And eventually little knots were formed in this accretion disk and little clusters and clumps. And clumping is a really important thing. And the clumping occurred and allowed the accretion disk to have separate little clumps that are orbiting the star. And as we talk about this and we look at how this all works, okay, accretion disks are interesting because these are the way in which planets would form around a star. They're the way in which asteroids might form, dust might remain, or in ways in which we might get planets in a zone around the star that might be habitable for life. So that's kind of interesting how that works, and I really think that's kind of neat. So that's what accretion disks are, and so I want to actually open it up here to Tara or Daryl or even Amanda here, because you asked a lot of good questions too, Amanda. You're just always so quiet. If you got any questions about this or you want to add to it, feel free. This is a good place to do it, I think.
Well, I have a question. Maybe we can talk about the D words, Mark, because you're talking about all this dust.
Yes.
But there's all that dust out there. I kind of get confused, or it just depends on how it's being used, but dispersion, diffraction, deflection, diffusion, and I think there's even scattering, and they all seem so similar, but they're not. And how do those terms relate to astronomy or what we're looking at in these nebula and the dust?
Well, okay, if we're looking at the nebula with the dust,
or any of them.
Yeah, I mean, we wouldn't necessarily talk about dispersion except for what happens to light passing through the dust or through something between our galaxy and another galaxy. We've seen that, and what is dispersion? Dispersion is the stretching of a spectrum so that different wavelengths arrive at different times to our detectors. And that difference in time is something that tells us an awful lot about what it passed through. Dispersion is very important when we talk about fast radio bursts, the millisecond pulses that we see coming from distant galaxies and now even our own. And so that's something that is very important. And diffraction is, again, usually we apply typically diffraction to optical phenomena. Okay. And what was the others you said?
Sorry, I was on mute.
Yeah.
So there was dispersion, diffraction, deflection, diffusion, scattering.
Okay.
Type of things.
Okay. Scattering. Let's take scattering because deflection and diffusion, deflection and scattering could be confused for the same thing. And I'll explain. And Daryl, feel free to jump in if you'd like to. But scattering is something that happens to high frequency light, especially in a low density medium like a nebula. Okay. And to give you an idea how that works, let's take this picture again. Okay. See that blue nebula at the top?
Yeah.
That's blue
the
because
Christmas tree, yes.
That's right. The Christmas tree, right. The upside down Christmas tree, as you pointed out.
Right. Mm-hmm.
Okay. Somebody knocked over the Charlie Brown tree. The blue color has to do with the fact that there is exactly that going on, scattering. It's blue for the same reason our sky is blue. Our molecules in our atmosphere, lots more of them than there is in this nebula, have actually, for the sunlight coming through our atmosphere, the high frequency blue light of the red, orange, yellow, green, blue, indigo, and violet spectrum, that blue light is absorbed and kicked out in all directions by these molecules, rather than left alone to go unimpeded. Okay, which was what happens to the rest of the light. The red, the orange, the yellow, the green, and so that means that the light in the sky has this blue cast all the time, just like in the nebula that we just saw. It's blue for the same reason. There's scattering going on there, but it's not being scattered by nitrogen molecules or oxygen molecules. It's being scattered by the dust grains, which have a way of absorbing and kicking out the light. And as we'll see, those dust grains get changed by those impacts into other compounds and molecules that could be conducive to life. See? So that's, in a sense, that's sort of a deflection, okay, where the light comes in and goes out another direction, but it's going out in all directions. So The proper term is Rayleigh scattering. Okay.
Rayleigh scattering.
Rayleigh scattering, yeah. Daryl and I have talked about Rayleigh scattering and Compton scattering in some of our streams before. If you notice, the clouds are white, right? And the sky is blue. How come the clouds aren't blue? That has to do with the fact that with that particular kind of scattering, the clouds absorb all the light and kick out all the light. And therefore, we basically see the full spectrum, which is white, coming from the clouds.
Right.
That's why the clouds look white. Okay.
Interesting.
So that's kind of cool, yeah.
We
It's very
actually
cool.
have a question from chat
Sure.
from our good friend Isabella.
Isabella.
Yeah, she wants to know why planets and moons have different chemical compositions.
They
Interesting.
don't necessarily.
Ooh.
Earth and Earth's moon have a surprisingly similar composition.
Yeah, that's correct.
Now, when you go out and look at gas giants, they are different.
Yeah.
So is it the atmosphere that makes them look different?
No, it's the manner in which
Time
they
at birth.
formed.
Yeah.
What's that? What'd you say, Amanda?
I was going to say time at birth.
Yeah, no,
so that makes sense. You know what I mean?
No, you're right. Because here's what we thought. We thought that rocky planets would form closer to a star, gas giants further out. Why is that? Because the gas giants have a lot of compounds we call volatiles. What are volatiles? Volatiles are things like formaldehyde and methane and ices. Okay, things that we see on comets, different types of ice, right? Carbon monoxide ice and CO2 ice. Water ice is a volatile because it can be melted and evaporated away under heat. So we thought that maybe the rocky planets would form nearby, and if they had any of these volatiles, they would have gone away. Well, it's true of Mercury, not true of Venus, not true of Earth, not true of Mars. So that theory was always sort of on poor standing, right? But it does serve to point out that the way planets form around a star depend more on the composition of the nebula from which they're formed. And so there, in this particular case, in our particular case, there are a lot of rocky silicon-based minerals in the solar nebula that ended up forming the rocky planets, and then a lot of gas that was retained by the larger mass of the planets as they grew. And this mass of gas that was retained became the atmosphere. And the atmosphere becomes changed by the geological processes that happen to a giant ball of molten silicate lavas and magmas and so forth over time. And once it starts to cool and forms volcanic surface with volcanoes spewing out steam and sulfur dioxide and all these other noxious, nasty compounds that we could never breathe, the atmosphere gets changed little by little. And it turned out that for us, we got lucky. We had a lot of water that could stay in puddles. These puddles became oceans. And when those puddles became oceans, we actually were able to foster phytoplankton, which started to make oxygen at the expense of all the CO2 that was in the atmosphere. So they would suck up the CO2 and pump out oxygen as a waste product. So effectively, you're actually breathing bacteria poop.
Well, that's their respiration, right?
Yeah, that's right. Respiration. If you remember your earth science, it was respiration and transpiration. Respiration, where they make oxygen, and CO2 is actually in part generated during the transpiration process, and a little oxygen is used. But for the most part, the plants do a lot of their work during the daytime. And so when we see the phytoplankton at work, well, we look at a planet that's got a lot of oxygen. It keeps getting pumped into our atmosphere. And because that keeps happening and it keeps getting pumped into the atmosphere, we are still here. If that stopped, our oxygen would eventually dwindle, and so would we, right? So that's something that you see happens. And that process is something that makes a lot of sense when you think about the chemical components in the solar nebula, what first formed. Okay. But as Daryl mentioned, okay, The gas planets out in the outer solar system, well, they've got like Jupiter, for instance. Jupiter is made of mostly hydrogen. There's a little helium, and its core is also hydrogen. It might be a rocky core deep in the center, possibly. But the outside of the core, the outer core of Jupiter, is actually a very strange constitution that we can't even think about because we have no daytime or daily analogy to understand it. But it's hydrogen, but it's so compressed that it actually is conductive. And so it's called metallic hydrogen for that reason. It's really not metal, but it acts conductive like metals do. And this is partly why it has such a magnetic field that it does. It has a magnetic field 20 times ours. So it's actually quite a big planet with a big magnetic field. It also means that its magnetic field traps more solar particles from the solar wind. And that solar wind becomes radiation belts around Jupiter, just like we have radiation belts around the Earth. Those are trapped particles around our Earth from the sun to get trapped in our magnetic field.
Van Allen belts.
You got it. The Van Allen radiation belts. And that's, and then we have people that say, well, we could never leave Earth because we'd have to travel through the Van Allen radiation belts. Well, you're not in the radiation belts for long. And yes, in part we did. And we made it. We got there and back. Right. But it is dangerous, and it is dangerous to our health. We could have problems if we travel through the Van Allen radiation belts at a solar maximum when there's so much going on in the Van Allen radiation belts that there's so much trapped particles that we'd get nailed with this high energy radiation going through. We do have to be careful, So, there are reasons to be careful, right? So the planets then break down by the solar nebula and what makes them up. Okay. So, and I think, Tara, we ended I think that was your question, right? I don't think there's money left there.
No, I think that's great. I appreciate that.
Okay.
I've always found it curious that in our exoplanet searches, we have found other solar systems. I guess you should call them stellar systems because it's not our sol, the sun.
Yeah.
Other systems have the big gas giant planets close to the sun. Hot Jupiters, they call them. How the heck did those happen? I mean, did they form close to the sun? Did they form farther out and then migrate in? Planets change orbits sometimes, depending on what's going on in the system. That cosmic game of billiards going on. But I just thought it was interesting that, there are such things as hot Jupiters out there around other stars.
Yeah. And some of our satellite studies have actually been able to characterize the atmospheres of these hot Jupiters to see kind of how the winds move on these things. And you say to yourself, well, how could it actually form there in the first place? And the answer probably lies in one of two things. Okay. First, the second thing you said, Daryl, I think is something that did happen, and we have an indication that that's true, and that is that some of these planets formed further out, but spiraled in to closer to the star over time because of events that occurred in that system. We see there's at least several giants that are bigger than Jupiter that are basically leaving a trail behind of their debris as the star is dissolving them. All right, and they're being evaporated. Mm-hmm. So they're losing a lot of mass as they orbit the star. So eventually, that planet will be gone.
I assume you could look at some of those as almost failed stars.
When people mention,
if it was bigger, it could have been like a binary star. But it wasn't big enough, so it fell in. But now it's getting eroded away by the solar wind or the heat, radiation, whatever from the parent star.
All the above. Yeah.
Well, there's an interesting comment here in chat from Ian out in Liverpool, England, getting late out there for him. It said years ago Jupiter was gas. Now it seems to have a core.
Oh, that's because of our understanding. Thanks, Ian Kendall. Ian's a good guy. He's got a lot of good observations he's made. Yeah. Jupiter always had a core. It's just that we didn't have enough information. We have to visit and to use instrumentation, try and detect what's going on beneath those cloud decks. And with the Galileo probe to Jupiter, we were able to acquire a lot of information, including the fact that it, along with Saturn, do have this metallic hydrogen core or outer core going on. And that's something that was always there, but we just couldn't detect it. We didn't know.
So
And go ahead.
are you saying that will eventually erode away too?
No, I'm saying that
Okay.
it was always there. We just couldn't detect it.
Okay.
Yeah, and that's the problem. Our science is only as good as what we know.
Mm-hmm.
It's interesting. There's an old saw that Saturn, differentiating from Jupiter, its density is less than 1.
Yeah.
And
It's
what
float.
has a density of 1? Water.
Yeah.
If you had a big enough bathtub, you could float the planet Saturn in that bathtub.
Yep.
Wow.
It's like imagine a styrofoam ball on water. It just sits right there and barely goes down in, right? That's kind of how Saturn is. Really interesting. Now, Saturn's core, of course, is massive compared to the Earth. But overall, the overall density would brings us, the average density brings us to the point that's less than 1. And so we would end up having a floating planet, which is kind of cool because I'd actually like to see that.
That'd be fun.
That'd be fun, yeah.
Okay.
Good. Float
I
around
got-
the universe.
I
Yeah.
got one for you. I don't know if Kathy was here or not when you threw that pop quiz at me, but she's
Oh.
come to redeem me. We have a pop quiz for you, Mark.
Okay.
Kathy wants to know, what do these four stars have in common? Aldebaran, Altar, Antares, and Rigel. 5 minutes to break. Go.
Aldebaran, Altair, Antares, and Rigel. Were they 4 stars having
Did I
common?
pronounce them all right? I hope.
Yeah, it's Aldebaran, Altair. Altair is a white star. Aldebaran's a reddish star. Antares is a reddish star. Rigel's a hot blue O-type star. So they don't have their spectral classes in common. But Aldebaran is part of the winter sky. Altair is part of the summer sky. Antares is part of the summer sky. Rigel is part of the winter sky. So Aldebaran and Rigel are in the same sky, essentially. And Altair and Antares are in the same sky, essentially.
Aldebaran and Antares are both red.
Yeah.
Uh,
yeah. And
Aldebaran
Rigel are-
and Aldebaran and Antares are both, Aldebaran and Altair both represent the eyes of the figures, the animals in their constellations.
Yeah.
Something tells me this is a trick question that we've had before, and I want to say it's a movie reference, but I haven't seen all these sci-fi references movies.
Oh,
I see Kathy's answer, and it makes total sense.
I
Okay,
haven't
I'm not
scrolled down
looking.
because I didn't want to lose the question.
I'm not looking. I don't want to see. I want to look at okay.
I have
What is
not
4
looked.
stars having common?
Good luck, guys.
I think.
Oh,
If
okay.
the- wait, did you look, Daryl?
Yes, I did.
Oh,
Okay, Daryl's out,
I'm not gonna
Tara's
look.
out. I
I'm
didn't
not
look.
looking.
I don't want
Okay.
to move the scroll
I
bar.
remember that now that I saw it. Sure.
I
Me
think
too.
I
Me
think it was a
too.
a trick question for Mark, and I think Daryl knew it instantly and blurted it out, and that's why this seems familiar to me.
But it's
I-
kind of 'tis the season, perhaps.
I didn't blurt it out, did I?
Oh, I
No.
don't know. I don't
I
know.
don't think
I
you
don't
did.
think you did.
No.
Okay.
But
I think
yeah, I
you knew
get it.
instantly, though.
I get it. No, I didn't know. I had looked at. I've heard it before, but I forgot it. But yeah, it
I'd
makes perfect
forgotten.
sense now.
Yeah.
So this is,
I have a movie guess, but we're
So-
running out of time. And this must be painful for chat who've already seen the answer.
Well, it's kind of like the Star of Bethlehem you were talking about. I mean, it's something traditional. It's just a hint that we used to
well, see,
do around this time of year. So it's kind of related to that.
That's why they call it trivia.
They're not the
Mhm.
Yes.
names of the 4 horsemen,
Of the apocalypse.
the horses. Yeah.
Yeah.
well, Rigel would be a
Hope
great
not.
name. Aldebaran.
Well,
I think, was the
Antares.
name of a horse, wasn't it?
Antares. I don't know.
Yeah, Anti-Ares, of course. That's where the name
My
originates. Right?
mythology, yeah.
So Altair, I don't know. I honestly
I
don't
have
know.
a movie in my head. I haven't seen the movie, and I don't
Okay.
know what the reference would be. But
Okay, you know what? Kathy Prunasek, you got me. Okay,
hold
I
on.
didn't look. I
Merch
don't know
coming
the
up.
answer.
It's a Charlton Heston movie,
Mhm.
Oh no!
and it's not Planet of the Apes.
Oh, that's
I swear to God, I was gonna say Ben-Hur when you guys say Christmassy.
It kind of is, So
Kathy,
I
Great,
knew
you
that.
did
got
it,
me.
Kathy.
You
You
did
can
me.
go
You
into
got me,
the new-
Kathy.
that's
You
I
can
didn't
go into
know
the
that.
new year victorious. You stumped Mark. Stumped the chump.
Yeah, I mean, I remember the movie very well, but I did not know the name of the horses.
Oh yeah.
See, but again,
now-
I knew they weren't horses, like constellations of horses. So
Well, I think that she kind of. It was a trick question, Kathy, naughty, because she actually said, "What do these 4 stars have in common?"
they're
It
all
should have
names
been,
of
"What do
horses.
these 4 names have in common?"
Oh.
And then I still wouldn't have got it. You still would have won.
I
But
was
at least it
thinking
would have been more
horses, and
fair.
I was thinking Ben-Hur that it was a movie, but I couldn't.
Oh,
One day I'll
that's a
see
great
it.
movie.
That's
That's a
like
very good movie.
4 hours, isn't it?
It's pretty long.
was-
There's an intermission. You
That
can take a
and
break.
10 Commandments I haven't seen
Yeah.
yet, and I know Daryl stepped away, but it's
Kathy
someone
says it's
else's
on TV
special
right
birthday
now.
coming up this week, and
Oh, is that true?
I'm not talking the 25th. Yeah,
Oh, okay.
Nice.
so
Wow.
after this short commercial break, if you want to pour in your
Yeah.
well wishes.
All right. So
On that note,
I guess. I mean, it is time for us to take our first break, guys, tonight. We're actually going 2 hours straight with only a couple short breaks. Anyway, we'll be
you have
right
more
back.
trivia, get it in there.
Yeah, if you got more trivia, if you want to, throw more stuff at me, go right ahead. But I didn't say I was a movie buff. I said I was an astronomer. Yeah. Okay, but hey, we'll be right back after this.
Hello, who is it? How'd you get this number?
Hey, Ken. Hey, man, it's George. Hey, man, what are you doing?
Right now, I'm trying to chop ice off of my deck here before somebody breaks their neck. What are you doing today?
Me? Oh, ghost hunting. Hey, listen, Bill from KGRA wants us to do a commercial, a promo for the show for them to play. Got any ideas?
I don't know, man. I don't know if I want to film a commercial or something like that. Well, hey, why don't we just do a montage or something, like clips from the show, and just call it a day?
Okay, yeah. Just put a bunch of highlighted parts of the show. Not a problem. I'll take care of that. Listen, have a great day. I'm almost done here.
Yeah, all right, man. Let me know how you make out, all right? Yeah, you bet. Be good. I'm okay.
Tony, I love you.
I love you too. Yeah, you know what? That's why I hate when they say that old people in the Northeast are so rude. I'm like, you, I'm down here and I'm being nice, and everybody's like, not even a wave. I'm like, you're not going to get the coronavirus from waving at somebody.
A little close up view. Check this out. Hello. Hang on, let's get us on camera again so we can wave. Wave back, Robert.
Yep.
If you wait.
Robert, thank you. Thank you so much for sharing some time, inviting us into your home.
I co-authored a book with Andrea Perrin, if anybody was not aware of that.
No one is aware of that.
No, and I've never been to the Conjuring House.
I wrote a book
We're going to do this again.
with Andrea Perrin, and I've still never been to the farmhouse.
Did I mention I wrote a book with Andrea? I wanted to, it's over my shoulder there, and I've never been.
We took a 2-week absence from this, and now we're back with
to the Conjuring House.
Dude, I'm hiding, man. It's COVID. Oh, I'm sorry. It's
What's going on?
I love that blanket. I'm having blanket envy.
I know you are right now, right?
Yes.
Sometimes I move it around with my body. It's like Ouija meets Twister. In the middle of the night, I contact spirits just by rolling around on it naked.
Watch Dead Air on KGRADB.com Sundays from 8 to 10 p.m. Eastern, 5 p.m. Pacific.
And also, don't forget to check out KGRA YouTube and KGRA on Facebook for all the amazing shows, guests, and topics. Did I mention that I wrote a book with Andrea Perrin?
Hey, welcome back. This is Mark and Tara and Amanda and Daryl. I think we're all back, and everybody's happily moving forward. I want to thank Kathy for stumping me with that question. Amanda, I actually got the closest.
No. Yeah, but not because I knew it, because I remembered it. I feel like this came up this time last year.
Maybe. But, to keep... if Daryl, you got any commentary, I mean, you can throw that in. I'm going to go through a little bit of the James Webb here and talk about some more Dark Nebulae, but you can throw something in here if you have something to say about where we just were.
I used to know that. I forgot. I haven't seen Ben-Hur in a long time. They're the 4 white horses that Ben-Hur drove in the chariot races in Rome. Had the crash and all that stuff.
Yeah. That's where the spikes in the wheels were cutting into the spokes, right? They get too close. Tara remembers that. She's nodding.
Oh, it was very dramatic. We saw that in the theater when it came out. It was pretty awesome.
Wow.
Never seen anything like it at that time, right? I mean, now it's kind of,
Oh, that's okay. It's still a cinematic masterpiece.
Oh, it was amazing. Yeah.
One thing I'd throw out there, we talked about a while before the break at the top of the hour, was conservation of angular momentum.
Yeah.
When you look up in the sky at night, or in the daytime for that matter, everything you see is spinning. Everything. It's either rotating on its axis like the Earth does, to make a day, or it's revolving around something else like we revolve around the sun, or our sun revolves around the center of the Milky Way galaxy, or both. Everything you see in the sky is spinning. I saw just yesterday, day before, there's a rather old vid on YouTube of some college professor. He has a great big hoop with spandex stretched on it, and he sets it down horizontal, and he lays a weight in the middle, and he starts chucking marbles across the spandex.
I've seen that.
Yeah, and it's very informative. And he talked about why things tend to wind up all spinning the same direction, and he gives a graphic demonstration of it on the spandex. It's well worth watching if you could find it.
Sure.
I wish I had a link, but I don't offhand.
Yeah. And it's interesting because that relates to the accretion disk we were talking about before, which was this guy right here. And, people have to understand, how this actually works, If we talk about the accretion disk, okay, we're talking about a infalling material. It comes from all directions. So the hard part is seeing how that becomes something moving in one direction around a central object. And that has to do with the way when they're falling in, okay, some of the particles are going to, because the universe is not even in all directions, because this debris is coming from all directions, some of the particles are coming in along the same path, and they're going to start to curve in the same way. And now you have, say, 2 particles. And if you have 1 particle out here, these 2 particles have a higher amount of gravity, higher mass, and eventually this 1 particle is going to get drawn into them. And now you have 3 particles moving around and heading in a particular direction. And then those 3 will pull in a 4th and then a 5th. And over time, you end up with one predominant direction that everything moves. Now, we noticed in our solar system that not everything is going the same way. We have planets that, that rotate, tumbling like this, okay? And Uranus, for instance. We have planets, minor planets that have very long elliptical orbits and are higher elevations to the relative to the ecliptic where all the planets are. So, and we have a cloud of comets around the whole solar system in every direction, and they orbit in their own way, all right? But if they get into and get tugged on and move toward the inner solar system, they will tend to even out and will tend to fall into the accretion disk. And that's kind of what happens with these dark nebulae.
So, Mark, is there a point in time when the disk has to flatten? Because if they're coming in from all direction, isn't it a sphere? And what triggers that to happen?
Well, we talked about before, if you have 1 particle, okay, and another particle, there's no reason why they should ever flatten. But if 2 particles are in a similar path, this 3rd particle is going to end up drawn into that path and might eventually, and that's exactly what happens. They actually call it flattening. Okay, the accretion disk will start to flatten, and the particles will tend to then fall into the middle. The particles out here that are moving in a different direction will interact with the particles near the middle of the accretion disk and either get ejected from the system or moved in their orbit until they generally end up back into this accretion disk rotation. Okay, and again, it has to do, as Daryl mentioned before, with something called conservation of angular momentum. That's a whole class in itself if we're going to make it a class. But really what it means is it's the momentum the momentum is what's called mass times the velocity of an object. So if a moving thing is moving at a certain velocity, it has momentum. Ta-da! If you move it, if it's being curved in a path, it's angular momentum. Okay? So if gravity down here, a bunch of particles are tugging on something out here, as it comes in, it starts to curve in. That curving motion is assigned angular momentum. And every single object in the universe, like Daryl said, it's either revolving or it's orbiting or it's rotating. Okay, they also have angular momentum. Okay, we have angular momentum going around the sun. Okay, the clouds have angular momentum, the particles moving within the airstreams. Okay, everything has angular momentum that we can see because you can always assign a direction of rotation and a change to that direction over time. And that change is where you get your angular momentum from.
And it's often expressed in the sense of being as part of a system, like the Earth-Moon is a system. Yep. The total momentum of the Earth-Moon system is constant. It's conserved. And as Mark said, this is getting into a topic for another time, but you've heard the moon is slowly moving away from Earth because of tidal forces on Earth. The moon is moving a couple of centimeters farther away every year. And, this is why the Earth used to have an 8-hour day and it now has a 24-hour day. The moon was a lot closer in the past, but it robbed energy from the Earth via the tides. And that made it move away from Earth.
Yeah.
The total energy in the system is still the same, though.
Right. And if you want to see that sort of in a way that you might be able to understand it, if this is the Earth and with the tidal bulge sticking out like this, as the Earth's rotating, the tidal bulge is kind of in a direction that's just ahead. So if you think about it this way, as the moon's going around the Earth out here, okay, the tidal bulge is sticking out kind of ahead of the moon's orbit, and it tugs a little bit extra on the moon. I know it's a small value, but over billions of years, it makes quite a difference. And so that extra tugging gives the moon additional momentum, but that additional momentum and motion actually then takes it away because of the attraction between the Earth and the moon, robs the Earth of that similar amount of momentum. So they're trading momentum. And thus, that's why the Earth's rotation rate is slowing down over time. We actually had a 4-hour day at one point. Okay. And then with the birth of the moon, we ended up going to 8 to 12 to 18 to 23 hours, 56 minutes, where it certainly currently sits. Okay. And then the moon is moving a little further away because of that. And you might ask, well, is there ever a time when the moon will be free of the Earth? Well, left alone, if the sun didn't have any issues, then yes, there would be a time billions and billions and billions of years from now where the moon could actually escape the Earth-moon system. However, the sun will be dead long before that. So we won't ever see that happening. But that's exactly that process that Daryl was talking about, that I'm talking about. Angular momentum is the reason why things become disks, okay, moving around, because of the reason we mentioned before with the particles all tending to a common rotation disk. And that's how that works. Now, these accretion disks, okay, may eventually allow a star to form in the center. And thus they'll be clumpy, possibly outside, and they might allow planets to form, and planets with moons, you know. Now, when we look at these dark nebulae that we're talking about, one thing to understand is that we can't see what's going on inside them, not with our conventional telescopes. The Sky Tour live stream telescope out west in the desert in Arizona cannot see inside the dark nebula unless they're very thin and we can see through them. Okay. So what we're talking about is needing a telescope that can see inside these dark nebulae. Well, we have two possibilities. These nebulae can also be viewed in the radio spectrum, because radio waves that are generated by any objects in there can be seen, and we can actually record those radio waves, and we do. Okay, we get radio imagery of these objects. Radio is light. I don't know if you knew that, but it is. It's just light way out in the red end, past the red end of the spectrum. Okay, all right. So out past microwaves and so forth. And if you look at the other aspect, the other possibility for seeing inside these dark nebulae is by using infrared systems. Now, infrared energy is very easily stopped by our atmosphere. So we don't have a lot of infrared telescopes at the surface of the Earth. On high mountaintops, there's infrared instruments. But one of the best instruments for us, which is going to launch on December 24th on Christmas Eve, is this guy. This is the James Webb Telescope. Yes, it's launching, Daryl. I'm sure it is. Aren't you?
I'll believe it when I see it.
I'll believe it when I see it, yeah.
Do you think the first image is going to be Santa en route?
No, actually, I hope the first image is not a reindeer splattered on the face of the telescope. That would be bad.
Pigeon.
A pigeon, right? Oh.
It's going to take about a month to get out to the L2 point, Amanda. Yeah. And you won't see any images before then.
Yeah, it's still going to be folded up until it gets there, as my understanding is. And so you also may notice that the mirrors are gold. Okay, those are called segmented mirrors. They're little hexagons, and they all fold up. You can see on the left side, you can see that this mirror system right here in this view is in the process of folding one way or the other. And you can see the crease between the mirrors. It's a thick black line, a zigzag line going down the left side to the right of those first three segments.
Right.
That is the folding half that goes behind that set of mirrors in the middle. And then the right side does the same thing. And then you can see that those stalks that you see just to the left and right there that go up to a top piece, that's the folded horn of the antenna. Basically, it's the secondary mirror location that's going to fold out and form the rest, and I'll show you that in a moment. But this telescope is really interesting because here you see it folded up now. Here you see the two halves folded up. You see these mirrors on the right there are folded behind, and the mirrors on the left are folded behind. Now it's in that launch configuration, but what you still see is this silver thing along the bottom there. That silver thing is the sunshade. The sunshade is very important because this is an infrared telescope. Infrared energy is how we're going to see what's going on in there and in these dark nebulae. And we're going to have that sunshade required because we have to block out the Earth, the moon, the sun, because those are sources of infrared heat. And the sensitive instruments on this set of packages inside this telescope are so very powerful that we don't want anything to impact the sensor package. So that's why this silver sunshade here is so important. All right. Now I mentioned the gold of the mirror. It's gold plated for a reason, and it's really gold. And the reason is because gold is unreactive. It doesn't react with other rays like cosmic rays striking this. And there will be lots and lots of cosmic rays of varying strengths hitting this mirror. Well, gold is unreactive and won't happen, and we won't get much happening with that. Next, gold is an excellent infrared reflector. It reflects infrared energy very, very easily and very well. So that's why these mirrors are gold.
Well, should point out they're not solid gold.
No, they're coated.
It's just like when you illuminize a visual optic on a visual telescope. A little bit of aluminum or a little bit of gold goes a real long ways.
That's right. It's like a vapor deposition process that puts the gold on there. If they were solid gold, they would have been stolen already. And James Dugan actually had a funny comment. He says he's getting, James Webb delayed launch disillusionment syndrome. Yes, I think you can join Daryl with that, James. James is a longstanding member of our SkyTour live stream. Thank you, James, for coming out. It's good to see you. And Isabella says the Webb will be the most beautiful device in space made by humans. It will be probably the one that detects life on other worlds, to be honest with you. Okay, because it has that capability of doing that. Because
I heard somebody knocking on wood.
What's that?
I heard somebody knocking on wood.
Oh, that wasn't you?
Me?
You were knocking on wood?
Well, maybe.
Tara.
It wasn't me.
Okay.
I will believe it when I see it, okay? I was born and raised in Missouri. You got to show me.
The show me state, yeah.
As ever,
Okay.
I'm just so concerned. The web is so darn complex.
It is.
And we're sending it 1 million miles away where we can't get at it to fix it if something goes wrong.
That's right.
Everything has to work perfectly when that sucker gets out there and unfolds and shakes out the sunshade and everything else. One thing goes wrong, and we just threw $10 billion out into space.
It's only money.
Okay, stupid question time.
Stupid questions.
The public will be allowed to see this launch, right?
Of course.
Oh yeah,
we're going to stream it. SkyTour live stream is going to stream it.
Well, I was hoping, but I mean, it's just been such a long wait, and everyone's so nervous, and I mean, God forbid something went wrong. The devastation, like they might be keeping it hush hush and just like
shame on
the
you,
professionals kind of watch and
keep your fingers crossed. That's all we can do.
It won't be hidden. It won't be hidden.
I mean, it is long over time. It's far over budget. Let's just hope they got their act together.
Yeah, I mean, right now,
pre-launch nerves maybe, but I'm nervous. Everyone is, but
Christmas
we're due for
Eve.
something awesome. So
yeah, I'm literally not going to go anywhere Christmas Eve because I want to follow the progress of this once it gets there.
And I forget the exact time. Was it 7:40 a.m. Eastern?
Yeah.
It's sometime in the morning after 7 a.m. Eastern. I don't know if it was 20 after or 20 to 8, but
yeah, as an astronomer, I'm actually going to get up at that early hour. Can you believe it? I'm usually up until 1 or 2 or 3 in the morning, but I'll be up at 7 and ready to watch this launch and stream it. And it's going to be nerve-wracking because honestly, it is the biggest. Hubble wasn't as big as this. Okay. Hubble was hobbled when it went into space. It needed glasses. Okay. It needed glasses to be added by the space shuttle, and they did it. But it's in orbit. They could do it. as Daryl says, there's over, I think, is it 1,000 different operations that have to go flawlessly for the Webb to work. However, keep in mind, they said the same thing for a similar amount of things that had to happen to get the Mars rover onto the surface. And the Perseverance rover landed just fine using technology that was new, used before, the Sky Crane, but still nerve-wracking. And I remember watching it go, and I swear I probably cried when JPL celebrated that it was on the surface safely. I was just like, wow, that's so amazing. I was breathing a sigh of relief. Right?
That's awesome.
That's because it really is so important, you know. And the Webb telescope is important because these dark nebulae we've been talking about, these locations, these regions in space are the place where life will start when it does. It's not going to start in these bright nebulae, okay, like this guy. Okay, this is not where life is going to start in a nebula like the Rosette Nebula. The reason is because the nebula is glowing because of hot ultraviolet radiation that is spewing out of that star cluster in the middle. For life to actually proceed in such a location, it would have to be shielded from all of that. All right. Now, it's possible that a dense enough dust cloud could shield some of the ultraviolet, but it's not likely. However, these clusters don't stay in the same place. Once they form, they interact gravitationally and eventually whip themselves away from each other. And then those gas clouds no longer glow because the ultraviolet energy is dispersed and not there anymore. And that's when we get the possibility that other development and other planetary systems and stars can form in a way that might be conducive to life. Now, these dust grains we're talking about, all right, first of all, let me show you what the Webb telescope, it looks like this when it's completed, okay? There's just a little GIF. You can see the sunshade is the silver part down below. You see the mirror, and you see the secondary mirror on that stalk. I watched a video of the entire process by which it opens up, and it's really quite elaborate and stunning to watch the shade open up. And I go back to watching Skylab unfurl its solar sails one time. In Skylab, years and years in the 70s. And one of the panels didn't work on the Skylab. And so it literally had only half the power. And then they had to put this umbrella up on it to keep the sun off it. You remember that, Daryl?
Parasol.
Yeah, maybe Daryl remembers that. Okay. I just aged both of us by quite a bit. And when I watched that happen, I was like, oh, man, why couldn't we get that right? Well, the answer is because it was new technology. And as Daryl points out, the Webb is not new technology, but among the newest of technologies. The sensors on the back of the Webb are unlike any we've ever created. They can look at a planet passing in front of its star and detect what's going on in its atmosphere. We'll be able to detect whether a planet passing in front of its star could have oxygen in the atmosphere. And this could be inferred because oxygen you can't see in the infrared. Oxygen is actually in the visible spectrum, the spectral lines that we look for. But it can detect other things, other components. It can detect greenhouse gases. It can detect methane and carbon dioxide. And depending on the combinations of such chemistry in the atmospheres, we will be able to deduce over time whether the planet has an oxygen capability. And that's kind of important. See, so the Webb is actually an extremely important telescope for what we're doing. And when it peers into these dark nebulae, what it's going to see is, well, untold trillions of these. These are dust grains, interstellar dust grains. This is one. Now, I have to say this is not exactly the same kind of dust grain that you would expect in interstellar space. This is a dust grain that's collected from our solar system. And maybe the dust grains are a little bit different, have different compounds because we have several billion years of changes that have gone on in our solar system in which we know there's life. So this is a example of a dust grain. The dust grains are very small. If you notice, it says 2 micrometers, 2 micrometers, on the right. That's a very, very tiny grain, okay? And to see it, it has to be magnified 25,600 times to see it, okay? So that's showing you that we're looking at very tiny grains. But what these grains are basically little seeds. They're seeds for other atoms that can attach to them and form ices on top of them, all right? That's the most important thing that dust grains do. And in a supernova, many of the star's outer atmosphere components are dust at that time. And when a supernova occurs, much of that dust is obliterated and just reduced to plasma and atoms of a particular, carbon, oxygen, magnesium, or whatever. But in a supernova, 10 to 20% of the silicon-based dust actually survives the supernova explosion. And more importantly, 30 to 50%, almost half, of the carbon-based dust will survive. So we're carbon-based, remember? Stands to reason. Okay. Silicon-based, we talked about silicon versus carbon in a previous show and how silicon is right below carbon on the periodic table. And there's a reason it's in that row. Okay. Like that. And so you might think, well, there could be silicon-based life. But carbon is the granddaddy of all atoms. And carbon can bond and create more compounds than any other atom in the periodic table in its entirety. So carbon is where it's at. I'm a carbon bigot. That's right. Okay. I am. And I don't mind saying that. Okay. I think that if there's life elsewhere in the universe, it's going to be based on carbon. All right. I don't see any other reason or other way it can be based on another element. No other elements work. And we talked about this in one of the last show. But I was mentioning how these grains here are seeds. And here's why. This is a diagram of a silicon-based dust particle. And all this stuff means, if you look, you see cosmic rays coming in the green from the upper left, and they drive off some things that are reacted with it. You'll see that there's H2O. That's just above the top. That's above there. That's water ice. Okay. Then we have formaldehyde, H2CO. Okay. Which is going to be subject to change from UV light from hot stars nearby. Then we have methane, CH4. All right. Next down to the right. Then we have carbon monoxide, which gets driven off as a reaction product with the ultraviolet light hitting. And we have water being driven off. We have CO2, carbon dioxide, being driven off from heating. We have ammonia, NH3, that's being driven off. And then we have this other, methanol, CH3OH there. And then what's the purpose of all these? It just shows that a regular dust particle becomes the home of all these other atoms and compounds. And it's these atoms and compounds which make up the building blocks of life in part. And when those dust particles are part of a solar nebula by the trillions, well, then they actually are welcome seeds to a new planet that's forming. And then other compounds form as a result of the planetary formation. So this is what's really cool about this. And because interstellar dust is so tiny, you can have an awful lot of these little compounds on one little dust grain. And that's really how it works. That's kind of what happens. And now I think it might be a good idea to just show you some of these. I don't know if you have any questions, Tara, that you could ask now.
Well, I was just going to say that dust is it's so organic looking, in that you call it a seed. I thought that's kind of interesting because it's really cool.
It is, and it looks unlike dust we have on the Earth, because that dust is formed in the microgravity of outer space, right? So it has different look and feel, and so forth. So it's kind of cool. Now, what I'd like to do, though, at this time, I think it's important to allow Daryl to do his deep dive because I can't believe how long this is going. We've had a lot of other discussions going on, but today's deep dive with Daryl is going to be interesting because he has a lot to talk about, especially at this time of the season. So, Daryl, would you like to head into the deep dive?
I will. Give me just a moment here, and
keep in mind, I do have a lot of Dark Nebula to show. So, if you have Dark Nebula you want to talk about, feel free to call it out, and we'll go there and look at it.
Okay. My one window isn't coming up. I probably should have parked this over in the brand instead of under my screen. Okay, we'll just go straight to Stellarium tonight.
All right.
And here is my sky right now. And I'm going to back up a little bit. It's 4:40 right now, and here we are at 4:30 in the afternoon.
Do you mind if I make you full screen?
Please.
Okay, there you go.
I'm sorry. Okay. Well, the sun is setting right now, okay? And I've been starting over in the southwest lately. The sun is about to set. I'll go ahead and make the sunset now. Sunset at 4:40 p.m. here today in Colorado. Sun just set. But if you look to the southwest, you have to look pretty quick after sunset. Mercury has come up and joined the other planets in the evening sky. Mark was talking about the plane of the ecliptic earlier. That red line is the plane of the ecliptic across the sky. Mercury is now to the lower right of Venus. And if you go up a little higher, there's Saturn. And if you go up higher again, there's bright Jupiter. And here's Comet Leonard still. Comet Leonard has moved pretty much east of to the left of Venus now. I have been out looking. I have not seen it. I'm really disappointed. Comet Leonard was directly under Venus the night of the 17th. And I went out to look with the binoculars. And, of course, a cloud formed directly over Venus in the sky just south of it.
What kind of luck is that?
Yeah.
And now, I mean, Comet Leonard is actually at that elevation. You're looking at, 15 degrees above the horizon?
If that much.
Yeah, so it's caught in the murk, too, so it's hard to see.
Yeah. Now, Venus is finally dropping out of the evening sky. If I zoomed in, you would see Venus is a skinny little crescent now. It has rounded the corner in its orbit as seen from Earth, and it hung up there for a long time, but it's dropping now. It's dropping toward the sun, and it's getting faster as it gets closer. Yeah. Venus is going to pass between the Earth and the sun on January 8th, I believe. And by then, Venus will be down here hidden with the sun. Mercury, in the meantime, will continue rising higher, and as I going to change the dates now. You see Mercury continues climbing. And on about Christmas Day, or a little after, here's let's say there, the 29th, Mercury will be to the left of Venus. And they'll be getting pretty low toward the sun, but you should still be able to see them. And after that, we're going to move down. There goes Venus behind the sun now. But you see Mercury on the 8th. Mercury is moving really close to Saturn. It won't quite get up to Jupiter, but Mercury will be in conjunction with Saturn on, I guess close to conjunction anyway. But that's what's happening over there. And Comet Leonard is moving away from us now. It's going to get dimmer and smaller in the sky, and it's been photographing very well, but I haven't had any luck getting it visually. So that's so much for Comet Leonard. Now, the other thing I wanted to talk about, though, we'll go back to now. This is going to be a little different. Rather than swing all the way around to the south, I'm going to stay in the west. And here at 5:30, the sun is set. And we'll give it an hour or two. Here is Cygnus, the swan. There is Alberio. I'll show you the art. There is the head of the swan. Alberia is the eye of the swan. There is Deneb. Excuse me. This time of year at Christmas, the Northern Cross, the Christian cross, stands over in the west-northwestern sky. Okay, it's standing almost straight up, and it's unmistakable. Makes a very pretty picture, and it's sort of a sign of the season, I guess you would say. I'm going to leave it right there, I think, Mark, unless you still want to talk about dark nebulas, because when you do, from the objects you told me earlier, we're all going to be up in this part of the sky. So I'm going to zoom in some, and we can start right here.
Okay.
So what would you like to look at first?
Well, I'd love to see you take us first to the cocoon, which is in that region.
Okay. Bear with me.
That's okay. Because as Daryl's bringing these up, one of the things to understand is that these dark nebulae, there's different types. And if you think about it, there's no reason in the world that we should actually see dark nebulae, except for the influence on them by stars nearby or stars within them. So that's something that I think is really important for us to check out.
Okay, here we are, Caldwell 19.
Okay.
Take it away.
When we look at the Cocoon Nebula, this is one type of dark nebula. We see it. There it is. You see the dark nebula coursing across the screen. It's in silhouette against many other stars behind it. And then to the left end, we see that dark nebula doesn't just have dust grains in it. It also has hydrogen gas in it. And that hydrogen gas is being caused to ionize and, of course, glow. All right, because right in the middle of it, you see a star that's formed inside the cocoon, and that star has ionized the gas around it. It's sort of spherical, which is kind of neat. You can actually see that, but you also see these dark lines right next to the star. Those dark lines are, of course, these little tentacles or tendrils of dust that you see that have moved in front of the nebula behind them. And so this whole region is full of this type of material. All right. So this is the Cocoon Nebula. One of the things that we saw, you'll also notice that around the red edge of the nebula, you see some blue. Well, that blue is that scattering process I told you about before. The dark dust is actually now scattering the light out beyond the distance where it can ionize the hydrogen gas. There's still going to be hydrogen gas out here, but it can't be ionized because it's out past a certain distance, and the star's ultraviolet energy falls off in intensity the farther away it gets. So some of it will ionize, some of it won't. It gets to a certain point beyond which it can't ionize anymore, and all you see beyond that is a blue ring of where you're getting this scattering process we talked about, where those dust particles scatter the higher frequency light. So that's just a beautiful image of the cocoon. Probably one of the best we've taken with Sky Tour live stream. So Daryl, if you can, are you able to take us to the iris now? Because the cocoon is illuminated by the fact that it's seen in silhouette against the stars beyond it, and it's partially illuminated by the fact that there's a star within it that's causing the hydrogen to glow. And now as Daryl starts to dive into the Iris Nebula is a region of space where there is a star that's not hot enough to cause the hydrogen gas to glow, but it is actually an area that is hot enough, causing enough of material to be scattered by the dust. So you can see that the starlight is being scattered here by the dust. You can see also that the dust itself is actually brown, right? That's because it's not formed only of carbon. It's actually made of more than just that. There's a lot of material in here, all right? We saw in that image before All right. We saw that there's lots of different materials, a lot of different compounds. All right. We also have and that blue in this image here of the silicate core and then that blue around it, those are ices. We have ammonia ice, as I said, carbon monoxide ices, methane ices, formaldehyde ices, methanol ices, and so forth. That is what we see there. And when it's subject to being heated by a nearby star, things happen. Other things happen, and it can drive off materials and other molecules to make separate molecules of floating around inside the nebula. Now, this nebula is glowing blue again for the same reason the sky is blue. The dust grains are scattering the light, but notice the brown color from the base properties, the base color of these grains is sort of a brownish, blackish color. Many of them are carbon-based, many of them are silicon-based, right? So we see that here. It's really, really pretty. Now, I don't know if you're fixed for doing this, Daryl, but can you show Lynn's Dark Nebula? 1251.
Who's Lynn and why does she have a nebula named after her?
It's actually Lynds.
Oh.
Lynn's.
Is he the one that found it?
Yeah, it's actually a Dark Nebula catalog made by him. Yeah, so there's one by E. Barnard. Barnard has a classic Dark Nebula.
It doesn't work that way anymore, does it? If you discover it, you don't get to name it or name it after you, do you?
If you find a comet, yeah, they'll name it after you.
A comet, yeah?
Yeah, you can get a comet named after you. But if you're doing research on, say, a dark nebula and you notice something odd, then you can certainly get it named after you.
Oh, cool.
Yeah. Did you find it there or no?
He's on mute.
Oh, he is on mute, isn't he?
Can you name meteorites if you find them?
Meteorites are named by the particular fall.
Yeah, they're named by location.
Yeah, so like the Argentinian fall is the one that my meteorite comes from.
Okay.
So a particular fall, because a number of them fall in Argentina. Have fun. Comet Commander. Hey, go ahead.
Kathy's awesome. Thank you for that, Kathy.
Okay. Lens isn't working.
Okay, that's fine. That's fine.
These are all up in the same part of the sky.
Yeah, and that's fine, Daryl.
The northern end of the tail end of Cygnus and Cepheus and Cassiopeia, they're all right up here in the same part of the sky.
Yeah.
So just
there's a lot of molecules up there of stuff, as Daryl's trying to show. I mean, and it's just, Stellarium that he's using online may not know the Lynn's object the way we know the Lynn's object. So we thought it did, but this is what we're looking at here. Okay. This is Lynn's Dark Nebula. It's also known as 1251. Lynn's 1251, Lynds. And you can see here, you can see the stars through the fainter edges. And again, the density of the dust, remember, even in the darkest spots you're seeing here, is literally 100 to 300 molecules per cubic centimeter. But this is many light years long. Okay. And so, again, in some of these areas where there's concentrations like to the right of center, you see sort of a roundish concentration just below center to the right. That round black concentration could eventually form a number of stars and possibly planets around those stars at some point. And these stars don't have to be hot blue young stars. They can actually, they can be hot yellow stars like our sun, like our G-type star that we are, or K stars or M stars. The M stars are the most populous star in the universe. There's more of them than any other kind. And if you recall from our wonderful diagram here, not that diagram, but this diagram, they're at the right-hand end. As Amanda said, the hottest and bluest at the upper left, the coolest and smallest at the lower right. Well, there's more of those ones at the lower right than any other type of star in the universe. And in some cases, they're only slightly bigger than the planet Jupiter. There's actually one star that's been found that's smaller than Jupiter, but it's a lot denser. It's denser by more than 80 times Jupiter's density, and that's why it can actually be a red dwarf star like this. So there's so much the universe is teaching us, I can tell you. It's amazing.
When we look up at this part of the sky, you can see the Milky Way running up there. From bottom left to top right through Deneb and near Cepheus, Cassiopeia. You're looking along one of the arms of the Milky Way, and we see really rich star fields. We also see lots of dark nebulosity. And if you can think back to when we have shown you images of galaxies like M31 and Andromeda, or M33 and Triangulum, or the Sculptor galaxy we've looked at recently, well, you've kind of got all of it happening right here. When we see the little red regions, those are stellar nurseries. Those are H2 regions. When we see the bright blue areas, like you see down at lower right here, those are OB associations where the really big, bright, hot blue stars are cooking their lives away really fast. Yep. And then you see the dark lanes, okay? Well, that's the end result of what's going on in the pink or red areas and the blue areas. You wind up with the dark clouds. And that's where Mark is taking us, I guess, is where you see it's too darn hot down in the blue areas, and there's too much radiation in both the blue areas and the red areas. But when the blue stars blow up and reseed the galaxy with their material was down in the inside, it forms the dark clouds. And ultimately, that's where life is going to come from, right there.
That's right. And those grains, again, we talked about this, certain the 30 to 50% of the carbon grains will survive a supernova explosion, and 10 to 20% of silicon-based grains will survive. So there's a survival rate for these dark grains, but these grains then become seeds, as I talked about. Tara liked that term. These seeds then form a home for other ices to form, which is what the basis of our diagram before was that I showed you with our little grains, this guy right here. All right. And those actually are very important because they will eventually allow the formation of other carbon-based compounds because of interactions with cosmic rays, ultraviolet energy, and just plain old heat. So a lot goes on there, Now, in terms of looking at other things, I don't know if you can bring up, if you can zip through toward the winter sky a little bit, Daryl, and take us to the Casper the Friendly Ghost Nebula near Orion. I want to point that one out. That one's
hardly Christmassy, is it?
Well, I guess, but I showed you the Christmas tree nebula.
Can we pretend he's Jacob Marley, the friendly ghost?
Okay, sure.
Christmas present.
Yeah.
I'm sorry, I was muted. No, Orion is very much a Christmas constellation. Orion is up at sunset now. Orion crosses the meridian before midnight, actually, now. The green line is meridian, and is an evening object, strictly speaking.
It is.
And let me get back to it. I'm sorry, I got too many windows open. But, okay, and Orion is followed by Sirius, which is, if I want to talk about Christmas star, I'd have to say Sirius is it because it's really pretty.
It is.
Twinkles red and blue.
Yeah.
And, okay, here's Orion. And which one are we looking for?
The Casper the Friendly Ghost to the left. And that's that should be known to Stellarium.
Okay.
Interesting.
It's not showing me.
Okay, but it's to the upper left of Betelgeuse. It's to the left of Betelgeuse there. If you go strictly eastward from Betelgeuse, if you zoom in, you probably will see it a little farther south. But I can actually show what it looks like, so we can just see what it looks like.
Carry on. I'm sorry.
No, that's fine. It's just,
Stellarium isn't cooperating tonight.
No, and we, again, some of the names are ridiculous, it seems. But the Casper the Friendly Ghost Nebula looks like this.
Ooh.
Isn't that beautiful?
Oh, my gosh.
It's mostly dust. And what you're looking at is you see this beautiful central, they're called reflection nebulas, okay? But they're really scattering nebulas. You know them as scattering nebulas, but they are reflecting essentially the blue higher frequency light back to you. And so that dust does that, and you can see some dark lanes crossing through there. And you also see the browns of this other material, these other compounds in the dust that on these ices and so forth. This is a beautiful location, and this is an example of a nebula that's illuminated by a bright star or two that happens to be there. That could be one star causing those two areas with a denser area of dark nebula in between. But we don't really know. We could know that if we look at it with the James Webb Telescope. So it'll be interesting to see what's really going on in there. We'll see stars in formation in these dark nebulae that we would not otherwise have seen, except with a very sensitive infrared telescope, which is James Webb.
Infrared sees through the dust clouds.
That's right. That's right.
Amanda, you had a question.
I did. Oh, it was a setup and you fell for it. I'm sorry, Daryl. I want to see something in Stellarium. Mark, if you could take that picture down.
Oh, sure.
Okay, well, whoop it on me and I'll try to find it for you.
I want to know what the sky is going to look like for you on your birthday.
Okay.
Because that's coming up.
Yeah.
Hint, hint, chat.
You don't seem too excited about that, Daryl.
I embarrassed him. I was trying to get Mark's attention so he would cue me in, and you walked right into it. I'm sorry, I didn't mean to set you up like that.
Oh, it's okay. My birthday is on the 23rd of December, folks. And I'll nudge it one more time here. Let's see. I'll set it.
Do you know the exact hour in and around time?
It was 10 o'clock or so.
Okay. Let's see.
But
where's the time zone? Same time zone from your birthplace?
Actually,
maybe we'll get someone in chat to do a astrology chart for him for his birthday.
No, thank you.
Okay.
Well, 10 o'clock, it would have been the same if I was born in the central time zone.
Okay.
And it'd be the same here in Mountain Time, which we're at now. But this is my sky on my birthday, December 23rd.
Very cool.
So Orion was flying high. Sirius was following him up.
No wonder you like
higher up, here's Gemini. And I'm going to mention this. I don't often talk about it. But I was an identical twin, okay? And that's why, even though I'm a Capricorn, I always feel a strong association with the twins in Gemini.
Very good. I like that. That's
why I figured you might know the actual time, because especially with twins, there's always, I was so many minutes older. Or
he was born 9 minutes before me, and he never let me forget it.
Well, see, that's what I mean. Yeah, you're confirming the stereotypes, but since unfortunately we won't be here, but you're getting a heck of a birthday present.
Well, then he would have been Castor versus Pollux.
This is true. Yes.
Yeah. Because Castor is the star that reaches the meridian before Pollux.
Pollux lived, okay? Castor died.
Yeah.
So let's not end on a downer.
Well, you're going to be celebrating another trip around the year right before James Webb launches. I think it's going to be a pretty exciting week for you.
Very cool. And
happy birthday, Daryl.
Thank you.
Happy birthday to our wonderful co-host, Daryl.
Thank you, everybody.
That guy there.
Eat lots of cake.
Yeah. And this is Orion that we talked about before. So you can see all the stuff in there. I did not take this photo with SkyTour. This was done. Daryl provided this. It was done a different location. But my gosh, it's beautiful. Yeah.
Anyway, we're out of time. Merry Christmas, everybody. Thanks
Yeah,
for
Merry
coming.
Christmas.
If
Merry
Mark
Christ-
streams the launch, please do join us.
Yeah, we're gonna stream the launch. I'm gonna
Happy
make
Christmas
sure I'm.
Fun.
and Happy New Year if we're not back before then.
Yeah, thank you for joining us, guys, and
Thank you for your support all year long.
yeah, we have great folks in our chat. We have great folks at
Yeah.
Skytra Livestream. So if you haven't subscribed for whatever reason, please go do so. You know, we have Tara on there with us too, along with Daryl and Amanda. So, and we're all there, man. We have a lot of time, a lot of fun time. So you guys have a good time, and we will catch up with you. I guess after the holidays, right, Amanda?
I think so.
Yeah,
In the new year.
yeah, that's it. All right, guys.
Ho, ho,
Ho ho ho! You've done
Happy
it again.
Christmas all.
Good night, all.
Good night,
Stay
everybody.
safe. Bye.
Bye bye.